Welcome to the Wolfram High School Research Program's special event where we're going to be displaying a bunch of student projects and getting to know the awesome things that some of our young students have been doing over the course of the last couple of years. This session is for students who attended our summer program, the high school summer research program, in the last 2 or 3 years, and then attended the Wolfram Emerging Leaders Program directly after that. And these are mostly projects that they have done as part of the Emerging Leaders Program, which is a 4-month, semester-long group research project over that's supervised by a mentor, and they work in a small group across that semester to accomplish some really genuinely extraordinary projects. So what we will be doing today is the students will be presenting kind of in their groups, and they'll get up and share their screens. In this session, each of the students has about just under 20 minutes to present their project and answer any questions that you have. So the first group that we are going to do is going to be Gregory and Christopher, who did their project on functional iteration and roots.
Yeah, this is our project on functional iteration and roots. I'm Gregory.
And I'm Christopher.
Yeah, so basically, in this project, we kind of expanded on the idea of functional iteration. So if you take a function f, you can compose it n times, and you get something called the nth iterative f, right? And so the idea is, instead of just iterating it like 1 time or 2 times or 3 times or an integer number of times, we wanted to explore what would happen if you tried iterating a fractional number of times. So for example, like a half, right? So what would that even mean? And so if you want to iterate a function a fractional number of times, you can kind of interpret it as being, right, f of x is equal to some sort of function. So the half iterate of sine of x basically would be the function that satisfies f of x is equal to sine of x, instead of the other way around, where sine of x is equal to a function. And so we kind of explored this using a couple of methods. The first 2 methods were analytic. So we just, kind of guessed a solution, guessed the form of a possible solution, and used algebraic manipulation to derive it. And so you start with something like ax plus b, which is an affine function. And for these, it's pretty easy to derive a general formula. Here it is at the top right. And so for monomial functions, where it's just, f, like it's just x or ax, you can also derive a formula, or x to the power of something. But for other solutions, it's not so obvious. It's not as easy. So for example, sine of x, there's actually no analytic solution. It's proven. Same for e to the x. So yeah, for complex polynomials with like multiple terms and not just monomials, it's also very difficult to find analytic solutions. But just as a cool thing, there's an example of one of the analytic solutions here. So the nth iterate of x squared is here. So this is the 1 plus ith iterate. So you can use this sort of function to get complex iterates as well.
Yeah, it's the zth iterate. So it's like plotting z across all iterates at 1 plus I.
Yeah. So you plug in 1 plus I and you get all the different iterates, and you get these really cool complex plots. But anyways, for all, it's not possible to get analytic iterates for all functions, so we had to do some numerical methods and estimate these iterates. So for example, like for e to the x, for general polynomials, for something like sine of x, right, you can't get the analytic iterate. So we have 3 different methods that we developed. Recursive function values, where you basically plug functions back into themselves and it kind of generalizes, and you find more values of a function, of the iterate. And then there's also simultaneous function value optimization, where you can use like a sort of gradient descent-like optimization to find an iterate. And then there's also genetic algorithm, where you mutate series like Taylor series or Fourier series. And to evaluate these, we sort of use like a loss function, which is kind of an idea from machine learning, where you just kind of, we take the iterate, or we compose the iterate with itself, the half iterate, twice, so we get the actual approximation of the function that it gives. And then we just subtract that from the original function and take the integral to see what the actual error was. And we square that, obviously, to make sure that the difference is positive, so we know end up with like a 0 difference.
Okay, so the first idea we explored was basically if you already know one point on the root of f, for example, x1, f to the 1/2 of x1, then you know that there's another point that must be on the square root of f, that is f to the 1/2 of x1, f of x1. And you can kind of continue doing this for kind of an arbitrary number of steps. And you get an infinite number of points that are all on the same function. So basically the limitations with this are that a lot of times these points converge, so they only give you an accurate solution around a very small area. And also you have to make that original guess. So even though it's two numbers, they kind of determine the amount of loss the entire function will have. So if we look at the results for this, basically it does work fairly well on a small number of function types. And within a small bound, it often works extremely well, like between, -1/2 and 2, kind of it seems to have a very, very good approximation. But just like the linear interpolation often comes out very jagged, and beyond the, extents of the function, it doesn't always converge. You don't always get a lot of points. So the next method we used was basically just make a guess for the root of f, and then if it's too high or too low at a specific point, just change the output of that point. And of course, that moves what the input will be, because these are, half iterated function or doubly iterated functions when you're trying to find f of x. So it doesn't always work. It's not guaranteed to converge. But if you do it, slowly enough with a small enough rate, it often gives a much better example. So we used our original guess from the previous method and just iterated it, 48 times. And eventually, in this case, it does diverge. This is the case of f of x equals sine of x plus sigmoid of x. But in the process of diverging, it actually comes upon a very good solution that has a very low error. But it's very susceptible to divergence and doesn't always give good answers.
Yeah. And so the final algorithm we use is genetic algorithm. So we take a Fourier series where it's a Cn x to the power of n, and then you just have a bunch of terms, or a Fourier series of finite length, and then so we mutate the coefficients in those. And so if you mutate the coefficients, you kind of arrive at a certain solution, and then you'd use the integral loss function to find the some sort of amount of best solutions, and then you mutate those, and it's a classic genetic algorithm. You keep mutating until you get a acceptable solution. And so the results for this are actually pretty good for functions that satisfy, that can be approximated like that. So for example, to approximate 1 plus x squared, the half iter of that, we got a very good loss, right? In the order of 10 to the negative 5. And also for something like sine x, if you want to approximate the half iter of sine x, you can approximate it with a Fourier series, and you also get a really good loss. But this does sort of diverge when you start approximating functions that don't exactly fit into the criteria of being able to be represented with a Fourier series or a Taylor series. So for example, if you add a sigmoid function, an activation function to sine of x, neither the Fourier series or the Taylor series really captures it too well, and so you end up with a slightly larger loss. And another thing is that some of these techniques are actually, these techniques each have different strengths and weaknesses. So for example, this one, the loss is a little bit bigger with functions that aren't exactly fitting into Fourier and Taylor series. But for example, if we used another previous technique like that simultaneous value optimization, then it would probably work a little bit better on the sine x plus sigmoid x. As you can see, it had a pretty good error layout.
Yeah. So the Wolfram language was super helpful kind of in doing this project for 3 big reasons. So first of all was just having a notebook environment where you can write down all your math formulas, all your theory, and also have your code kind of being integrated with that and being able to change stuff and work with all that. And the second was just algebraic solutions. If you want to guess at what the square root of the function should be, you can just guess its form and have, Wolfram Alpha just solve open bracket, close bracket, and figure out what those values should be. So for the affine function, I just guessed that an affine function's root is probably affine, solved, and it, figured out what the coefficient should be.
And you can also visualize really nicely. So, for example, another, affine function, the bottom left plot with the orange, the surface is a plot of all the different iterates. So the z-axis or the y-axis is like which iterate, and then the x and z axis are the actual function itself. So you can see how that you can visualize how the iterate changes if you plug in a different value. So like half iterate, third iterate, something like that. And you can also generate these nice complex plots and a lot of other stuff that's really useful when you're working with these sorts of functions. It's kind of hard to visualize yourself, but using Wolfram, it's much easier to actually see what you're doing with all of these functions. So yeah.
Thank you.
Do we questions?
Fantastic. Thank you, guys. Yeah, if anybody has any questions, you can put them in either the chat or the Q&A. But what was kind of the hardest thing that you did, or the biggest thing that you learned, or what were some challenges that you faced in this project?
One of the biggest things that we learned actually was just these numerical methods, because we started out trying to just do everything analytically, and we realized that it actually becomes really difficult, like really quickly, to go beyond anything like an affine or a regular monomial function. So having to use these like numerical approaches was actually really useful, and Wolfram was actually really useful to do them.
Nice. What was the kind of, I don't know, was there anything unexpected or kind of crazy that you weren't expecting this to happen this way? Weren't expecting to find this thing?
I don't know. I think it was pretty interesting how many like ways you could go about it. Like 3 methods that we presented, and probably more that you could approach it from. That all are, somewhat reasonable ways of thinking of how you might guess at these functional roots.
Yeah, there's definitely a lot more methods. These are just a few of the methods, and while doing this project, we also looked through some literature, and there are some other methods in the area for doing that could potentially work better for other results. So it's really not like a one size fits all sort of approach. You have to really find which method works better for your particular iterate, and then go from there.
Awesome. Fantastic. Okay. Looks like we don't have any questions for you guys. So well done. Thank you very much. Akshash and Sneh are going to do their project on double pendulum hashing. So some very cool computer sciencey stuff that we've got going on here.
All right. So this was Altrajanar's project. It's on chaotic hashing using double pendulum dynamics. And then the key idea of this project was if we could use a chaotic mechanism inherently as a source of randomness for a hashing algorithm, and that's what we kind of explored with the project. So you can go to the next slide. And yeah, so how Altrad and I are just gonna like split this in half. I'll talk about how we got the simulation working and the physics behind that, and then Altrad is gonna talk about how we took the results from that and then converted it into a hash function. So you can go to the next slide. Okay, so I'll just give a brief introduction on hashing and like the main idea behind the project. So hashing involves taking a string that you want, like a password, for example, and using some type of mechanism to convert that into a completely randomized string of characters that has no resemblance to the input. So the idea is you have a one-way transformation. And this is very important in things like password management and just security in general. And how this is normally done is you have your string, and then it gets a key part of it is this randomness aspect, which is crucial in converting the desired string into the output string. And what we decided to do is take that randomness step and see if we can put an inherently chaotic mechanism behind it. And the choice of that was a double pendulum in this case. And the advantages of this approach are we can tune the parameters for a maximum entropy and minimal hash collisions. And with Wolfram, we're actually able to like parallelize this computation, and this makes it resistant to structure-based attacks. So can I get the next slide? So yes, a little bit more on the chaotic dynamics and how we set up the simulation. So a classic example of this chaotic dynamics is a double pendulum. You can see that image there. And what the parameters for the simulation are the two angles of the two links of the pendulum, as well as the masses on each end, and then the lengths of those links respectively. And what you get is some couple nonlinear ordinary differential equations that we then numerically solve. And this will give us extreme sensitivity to small variations in initial angles and velocities, which we'll be able to see plotted in the plot on the right. So can I get the next slide? So as for how we went about simulating this in Wolfram, using a Lagrangian approach, we can take, which at its core is just kinetic energy minus potential energy of the system. And using this, we can get an equation for the motion of the pendulum in terms of the two masses, the two lengths, and x1 and y1 are or x1, y1, and x2, y2, the positions of the two bobs respectively. And we can get an equation for that. Going further, there's some derivations that have been done to get this equation on the bottom, which is, I believe it's called the Euler Lagrange form of it, I believe. And this is actually the equation that our simulation tries to numerically approximate, given the initial two parameters and other things like the damping coefficient and the gravitational constant. So these physical trajectories are then mapped to bit patterns, which Oxide will talk about later. And then, as I'll talk about on the next slide, we try to maximize the randomness that we get from this simulation. So as for that, we had this whole, the next part of our project focused on the parameter testing. So I mentioned how we could take a bunch of initial conditions and see how they map physically in the animation of the double pendulum. But the animation alone is not what's going to help us. We need actual outputs from this simulation. So testing a range of initial conditions and how they map to outputs was really the next part of the project. So on the right, you can see the image of kind of the randomness metrics that I was analyzing. In here are things like just viewing the plots over time, as well as a histogram to assess uniformity, and then a Fourier analysis to see if there are any periodic patterns. And the goal with this is the easiest way to see complete randomness is like a uniformity in the distribution to see that there's no like discernible distribution and that the outputs are all pretty random. And we kind of see that in this image. And the fun thing you can do with this actually is the physical constants don't actually need to be tied down to any like physical system. Since all we're trying to do is maximize randomness, we're not trying to get something that's actually physically possible. So the image on the right in particular has the gravitational constant -10, just to see what it would look like. And it turned out to be pretty good in terms of the uniformity. That histogram is pretty good. It's one of the best ones we got. And through this process, we tested different initial conditions and we found extreme variations or extreme sensitivities to small variations in initial angles and velocities, which Oxide was then able to use to as inputs into the actual hash function. So
Yeah, okay. So now let's go into a bit of our hashing approach. So our goal is to eventually create a hashing mechanism that uses double pendulum-based chaos to enhance randomness. And this hashing mechanism should involve both the physical simulation of a double pendulum, and we should be able to mathematically encode any input string into the physical parameters of a double pendulum. And the output should also remain 256 bits, which is compatible with standard SHA-256. So over on the right here, we can see a general flow chart of our hashing process, which I'll go into more depth later. But we start from the input string, and then we convert the characters of the input string into numbers using an ASCII conversion. And then we take those numbers and we map them to the physical parameters of the double pendulum. We then simulate this pendulum and solve the chaotic dynamics. And then now that we have this chaotic data, we normalize it, we convert it into bytes, and finally hash it through SHA-256 as a final sort of gateway into our 256-bit hash at the end. So let's talk a little bit more about mapping input to physical parameters. So each character in the input string is converted into ASCII values, and ASCII values are essentially just a table of values that correlates any characters into numbers. And numbers is really what we need here to map the physical constants of the double pendulum simulation. So using the input string, we determine the pendulum parameters like rod length, mass, or initial angles, and we can also determine the total time the simulation runs for. As in a double pendulum simulation, even very small parameter changes can cause large differences in trajectories, and this kind of clues us into the avalanche effect, which I'll talk about later as well. But since we can control the time of the simulation, we can adjust like the sensitivity to initial conditions through this as well. So now that we have our initial conditions of the pendulum, we can solve it numerically using Wolfram Language's ND-solve, which was very helpful in simulating the pendulum. And we record the velocity components and the angular velocity over time. I think you can see in the four graphs down in the bottom right, those represents the system's chaotic fingerprint. And the V2x and V2y values are naturally more chaotic because the second pendulum bob has much more chaotic behavior compared to the first pendulum bob. So now that we have this raw velocity data, we can normalize it into a bounded numerical range. And these normalized values are converted to bytes, forming a data stream that acts as the prehash. So now it's ready for cryptographic processing. And the reason why we have to bound it into a numerical range is to make sure it's suitable to be fed into SHA-256 as the final step. And as a side note, so if you don't know what SHA-256 is, it's essentially the industry standard hash function that's used for many data security purposes. So because of this final step, we ensure that our function has structural integrity and it's compatible with modern systems because of the many applications that SHA-256 is used in. And our double pendulum prehash just introduces an entropy-rich pre-processing layer that would improve the randomness of the hash function and make it more secure and more usable for daily purpose. So now that we have our hash function, which we named chaotic hash, we compared our function with industry standard hash functions like MD5, SHA-1, SHA-224, and of course SHA-256. So we tested on a multitude of metrics, including average Hamming distance, bit distribution uniformity, Shannon entropy, and statistical p-values. So first, let's talk about Hamming distance. Hamming distance just measures the avalanche effect of a function. So they take two very similar strings with only a single bit flipped, and you run both of those strings into the hash function, and you measure the variance in each of the outputs. So how much does changing a single bit of an input lead to a divergence in behavior? So it leads to an avalanche in chaotic behavior. So in this test, we only noticed marginal increases in our hash function compared to SHA-256. Also, a very big jump for MD5 because MD5 is it's like a fairly old version of a hash function, and it isn't really that comparable in security compared to modern hash functions like SHA-256. So then for another test, we visualized the bit distribution. So each histogram here shows like a histogram of how many bits are set to 1 across 100 different sample hashes. And we're looking for a flat bell-shaped distribution, which leads us to ideal randomness. And chaotic hashes histogram is on the bottom right there, and it's nearly centered and symmetric, which is comparable to SHA-256, while more older versions are like SHA-224 and MD5 show more irregular distribution. So, however, these qualitative descriptions are like, they're good, but we want more numerical answers. So we conducted chi-squared tests on these bit frequencies to obtain p-values. And what these p-values essentially tell us is how uniform the distribution is. So the higher the p-value, the more the outputs are closer to true randomness, which is what we want in a hash function. So as for our results, we noticed that chaotic hash did remarkably well in bit distribution, as it was 6 orders of magnitude higher of a p-value than SHA-256. So we can see that the double pendulum prehash actually helps to improve the randomness of the hash function. So finally, we tested for Shannon entropy, which quantifies the unpredictability of hash outputs. So here we saw that chaotic hash scored a 3.45, slightly above SHA-256. So again, similar to the Hamming distance test, only marginal gains in entropy, but it does indicate that a more uniform output distribution occurs when you use this double pendulum pre-hashing element. So with all of these tests combined, we can conclude that chaotic hashing is a very promising path for increasing data security and improving the feasibility of hash functions in the near future as well. And it can serve to basically highlight a future path towards cryptographic development. So yeah, thanks for listening. And if you have any questions, feel free to ask.
Amazing. Thank you so much. Great. Yeah, if you have any questions, please put them in the chat or in the Q&A. But what was the hardest thing, most challenging thing when you were doing this project?
I can get that. I think the hard part was trying to figure out how we can take this simulation that we'd made, because when we were doing the project, that part came out pretty quickly. It was, how do we take this and take these outputs and convert them into something that can be used in a hash function? And that took a good bit of brainstorming, especially, I mean, we knew that we had to use the positions and velocities in some form, but we didn't really know exactly how that was gonna end up in taking one character and turning it into another. So a lot of effort was like required there to make sure we had a good foundation for how we wanted to do that.
Yeah, for sure. Very cool. Excuse me. What was the biggest thing you kind of learned? Craziest thing, most strange thing that you found?
I think the biggest thing that I learned was probably just about the development of current hash functions. And I learned a lot about like how hash functions are like are tested for like a data security purposes. And I think the most shocking discovery that we found was in terms of the bit distribution results, where chaotic hash, like our function, did significantly better than the SHA-256 in leading towards a more random output distribution. So I think that was the most surprising thing that we found.
Very cool. Awesome. Looks like there's a question from Phil here. If Wolfram was going to tweak its algorithms that NDSolve uses between versions, would that hit the reproducibility of your output? It's an interesting question.
So if Wolfram researchers were to tweak the algorithms for NDSolve, I feel like that wouldn't hit the reproducibility of our output, because the main thing was about how deterministic our hash function is. Because it's the computationally simulated double pendulum, the same initial conditions will always lead to the same outputs, which is really important for building a hash function. So even if the algorithms for NDSolve were to change, I don't think that it would hurt the reproducibility, because the same initial conditions would still lead to the same output and therefore the same hash output as well.
Cool. Awesome. Okay, well done. Fantastic. Great job. Next up, we have William and Sandora, who did their project with Amaya, who couldn't come today. But they did their project on protein analysis techniques.
Hello, my name is William,
And I'm Sandora.
and we wanted to talk about our comparative analysis of some established methods for protein analysis and our own novel Monte Carlo approach. So this was a project we completed at the Wolfram Emerging Leaders Program in 2024. We worked with Dr. Sonnenberg to evaluate the performance and efficacy of several existing methods, and then we created our own method to address some issues we encountered in that process of testing existing methods.
So we implemented several established methods, including alpha complexes, calculating Zerni K moments, and various methods for estimating the internal surface area of molecules. And building on this, we developed a novel method based on Monte Carlo sampling to address pain points from our implementations related to internal surface area. So we begin with alpha complexes, which is basically a concept derived from de Lione triangulations, which are used to model molecular geometry and interactions. Here we represent a protein using its atomic coordinates and van der Waals radii. And further, we computed the power distances and checked for overlaps under a defined alpha parameter. We built what's called an alpha complex, which is a network of edges that reveals how atoms are geometrically connected and packed. And when we visualized these in 3D, we saw how overlaying van der Waals spheres with alpha complex edges helped us understand the molecule's spatial organization. So next we move on to Zernicke moments, which is a powerful way to quantify molecular shape. The structure of a molecule defines many of its physical and chemical properties. So quantifying that shape helps us understand how molecules interact or bind in different environments. Zernicke moments are basically mathematical descriptors that compactly represent 3D shapes and are also rotationally invariant, meaning that the same molecule will have the same descriptor regardless of orientation. And they're built using things called as spherical harmonics, which encode angular variation, and radial components that define how the shape changes from the molecule's center upward. So, using atomic coordinates and van der Waals radii, we first computed a Gaussian molecular density function. And after which we calculated Zernicke moments up to order n equal to 3 and normalized them using the Cantor-Archies norm, which basically allows direct comparison between different molecules. We also derived geometrical and statistical measures such as the radius of gyration, skewness, and kurtosis, which basically just describe how atoms are distributed spatially. And the heat map you see here represents the normalized Zernicke moments, and it visually captures how different molecular shapes vary in structure. So yeah, the molecule is shown here as well. It has a radius of gyration of about 3.26 angstroms, meaning that's the average atomic spread from the center of mass. So altogether, these results give a compact and rotationally consistent description of molecular geometry, which provides an advantage in drug design and molecular docking, especially in cases of where accurate shape and comparison matters.
So the next thing we tried to measure was the internal surface area of molecules, and we focused mostly on proteins. So this is a significant statistic in proteins because it quantifies the quantity or the magnitude of buried residues in a protein, and that can be very important during protein-protein interactions. It inversely correlates to the flexibility of a protein. So a molecule with lots of internal surface area would not be as flexible, and vice versa. And it also represents the accessible binding sites for small drug molecules that can actually manage to get in there and bind to those buried residues. It can also be used to measure the stability of a protein during folding and transcription. So the first thing we tried to address this was creating Voronoi structures between the atoms of the protein. So a Voronoi plane is effectively a plane that is equidistant between its two closest points, or in this case atoms, by constructing all of those planes and constraining them at their intersections with other planes within the bounding box of a protein. And you can't see the protein here, but there is a protein beneath all of these shapes. We can build a Voronoi volume, and by summing the areas of all of those faces, all of those constrained faces, we can establish a internal surface area. We found that this was incredibly slow in Wolfram language, Part of that was because we implemented it using Wolfram's built-in geometry functions, which weren't built for fast performance. But even when we tried implementing Voronoi algorithms on our own that don't rely on the more complex, more sophisticated geometry functions in Wolfram, we found it to still be much slower than we wanted. We also found that it was difficult to take into account atomic radii with this approach, although that may be possible with some modifications to the established Voronoi algorithm. The next attempt we tried was a significantly more sophisticated and, more importantly, modern approach, where we try measuring the occluded surface area of molecules. And we effectively did this by treating each atom in the molecule as a sphere with radius corresponding to its atomic radius. And then the intersections of those spheres were what we considered the internal surfaces. We used ray tracing to estimate those blocked or occluded regions. And by summing those total areas, we get the occluded surface area. This was accurate and relatively fast. It was magnitudes faster than the Voronoi interface method, but we still found it to be a bit slow when it came to large molecules, taking several seconds, which when we wanted to do batch testing was much slower than we could afford. So our novel approach was using Monte Carlo sampling. So Monte Carlo sampling, in more general terms, applies to scattering a whole bunch of points all over the place and determining the values at those points and using those to determine the value over the region as a whole. So this visualization you see up here is actually a way to estimate pi by estimating the area of a circle by sampling a whole bunch of points within a square. We found that our implementation that used these principles was 3 times faster when we estimated at high resolution, so lots of sampling points, very dense sampling points, and 50 times faster when estimating at low resolution. We also found that temporal performance scaled linearly with the size of the molecule, so it was ON. What that means is if you add an atom, the additional time it requires to compute the internal surface area scaled constantly instead of scaling exponentially, multiplicatively. We also found that it agreed when comparing 2 molecules on which had more internal surface area. It agreed with occluded surface in the vast majority of cases, and really only disagreed in those cases where the values were similar, and so the accuracy of our estimations fell apart a little bit. We also found, most importantly and most significantly, in my opinion, that low-resolution sampling was fairly on par with high-resolution sampling. We got a little bit more accuracy with high-resolution sampling, but the performant low-resolution sampling kept up pretty well. And so really the performance gains here are closer to the 50 times than they were to the 3 times. We can see that they correlate linearly here, the occluded surface values and the Monte Carlo values, and really we're treating the occluded surface as our truth. And so because it correlates linearly, that means we can effectively interchange the 2 methods and find that the results are fairly comparable. We also find that Monte Carlo is, more importantly, magnitudes faster temporally. So if we look at this bar chart here, the occluded surface timings are all the way up here at 6-point-something seconds, while the Monte Carlo timings at worst are at 1/5 of a second, and when going low resolution are far less than that. In fact, we even found this bar chart so hard to read because the timing changes were so fast that we linearized it with log 1000x. And even then, we see that there are several magnitudes of difference, especially in our biggest molecule and even in our smallest. So our implementation of this approach was to give each atom in the molecule a charge, which makes it effectively a charged particle, and to treat it like a physics problem more than a chemistry problem. So by using Coulomb's law, we can calculate the force, the effective force from each charged particle or atom in the molecule on a whole bunch of sampling points throughout the bounding box. And so then each sampling point ends up with some sum of forces, which is a direction and a magnitude. And we can treat the scalar magnitude of that force, of that sum of forces, to find the most balanced particles, effectively where the magnitude of the force is closest to 0, and use those as our surfaces, because those would be where the attraction from all of the molecules is most similar, and in other words, where they're equidistant. This is better than our Voronoi approach because we're able to define the charge as the atomic radii, which means bigger molecules, or rather as the inverse of the atomic radii, which means bigger atoms in the molecule and smaller atoms in the molecule don't have surfaces at the same distance. This is far easier to understand if you look at a visualization like this. We can see that each of the spheres here is an atom in the molecule. They affect a charge on the field where each color represents a different magnitude of force. And so we're able to strip away all of the sensors or sampling points where the affected force is too low. We're also able to strip away the points where the affected force is too high or it's too close to the molecule. And so we end up with those border points, those surfaces between atoms in the molecule. And we can take just a count of the number of samples that are here to approximate the internal surface area. And finally, as a bit more of a physical comparative analysis, we chose 40 molecules and we lined them up in pairs of 2, and we found the approximated internal surface area for Monte Carlo and for occluded surface area for both. And Monte Carlo and occluded surface area agreed on which one had the bigger internal surface area in 18 out of our 20 cases. Admittedly, 20 is a bit of a small sample size here, but because occluded surface area starts to slow down on those bigger batches of bigger molecules, we did really have the hardware to test bigger batches.
So, over the course of the development of the original article and this presentation, we received a lot of support from the team behind the Wolfram Emerging Leaders Program, or WELL. So, thank you to Dr. Jason Sonnenberg as well for his willingness to help us with anything we needed, from chemistry we were struggling with to opaque Wolfram documentation that we couldn't quite grasp.
We'd also like to thank the wonderful leadership team at WELL, including Rory Folger and Aaron Gillum, as well as everyone else at Wolfram who responded to our help posts, worked behind the scenes, and took interest in our project. We'd also love to answer your questions.
Fantastic. Very, very cool. Well done, guys. So while people are maybe typing a question or two, what was the craziest thing that you learned or discovered doing this project?
We had a bit of a lengthy research phase where we were trying to find different measures for protein analysis, and I think figuring out how outdated a lot of those measures was quite a shock to us. Even our most modern approach that we tried here with occluded surface area was from a paper from 1995, and in the 30 years since then, we haven't really had a better measure for that. And so we were asking ourselves really whether that was because there wasn't a better approach or just because the field had kind of stagnated on that region of study.
And adding on to William, most of these methods, including Voronoi, especially Voronoi, and even the occluded surface area method of estimating surface area, they're extremely redundant and also they're time consuming, as mentioned. And yeah, we want to develop a better method to approximate surface area, more accurately and also keeping time in mind.
Very cool. Love it. Jason, your mentor, asks, do you want to do more with proteins? If so, what?
If Sindora doesn't have an answer for that, I do. I would love to. I think this project was really interesting, and I think it also helped me as a TA at the high school summer research program this summer. One of the students there actually contacted me after the whole thing was over, asking for help on a research paper. So this kind of stuff really did help in figuring that out. Yeah.
And I think there's also a lot of potential in case of protein ligand binding And there's a lot of fascinating stuff going on with modeling and whatnot. So protein as a system or as a subpart of the entire like spectrum of biology, I think there is a huge potential because proteins are everywhere. Yeah.
Amazing. Great. Well, thank you so much, guys. I really appreciate you coming today and telling us all about your project. Very, very cool. Okay, next up we have Austin, Kevin, and Ritvik, who are gonna talk to us about their project that they did doing 3D printer infill with cellular automata patterns, which is pretty cool. I'm hoping for some fun visualizations.
Our project was on using 3D cellular automata to generate 3D printer infill patterns. I'm Kevin. Ritvik had the broken mic, and then Austin, you want to say hi?
Oh, hi.
So people know who you are. Okay. And then our mentor was Megan Davis. Okay. So, I'll just use the abstract as an opportunity to describe our project background a little bit. So everybody on the team had some experience with cellular automata, either by just doing a project with cellular automata or being in the Wolfram research program. And we had seen how one-dimensional and two-dimensional cellular automata were used to successfully model like real-world scenarios with stuff as abstract as like, just data encryption where the cellular automata is representing ones and zeros of any arbitrary data, or even things as concrete as like the spread of wildfires in 2 dimensions. But what we hadn't really seen was how 3D cellular automata could be used. Or we saw a lack of projects using 3D cellular automata. So how 3D cellular automata can be used to represent something in the real world? Well, kind of the obvious thing to grasp at is have the 3D cellular automata represent like a volume or structure. And then we started thinking about what type of structures in real life could benefit from this emergent complexity you're able to see in cellular automata. So we all came up with 3D printer infill. And if you don't know what 3D printer infill is, it's basically just when you print something on a 3D printer, you just give it like a 3D shell. There's nothing saying how it should be filled on the inside. So if you fill it with nothing, then your shape is going to be very weak and it might not even print because some overhangs might not be supported by enough material. But then if you take the other obvious solution, which is to just fill it all with plastic, then it's just going to take way too long to print. It's going to be a horrible waste of material. So an infill algorithm is the thing that specifies how to intelligently remove material from the solid version in order to keep as much strength as possible, but also saving material. And the infill algorithms available to us, like commercially, are just based on human intuition on what a good infill algorithm, like good infill pattern should be. So, for example, like some of these, they have names like gyroid, cubic. Like some programmer sat down and remembered that triangles are a strong shape. So they coded something to take in like an arbitrary 3D shell and then just fill it with triangles. But with only 12 patterns, you're not really going to be able to get something that is suited specifically to your needs. For example, imagine you were trying to print a joint that needed to bend between a 20-degree angle and a 30-degree angle. And anything above or below that, it needs to either like not flex at all or it needs to like collapse. That's going to be very unlikely with only 12 different patterns. And, what if it needed to be like 50 degrees and 55 degrees? It's just not going to happen. So at this point, what you can do is either sit down and try to design something to intelligently fulfill these specifications, or you can take advantage of something like cellular automata, which has billions of different patterns, but also has emergent complexity that might, by random chance achieve what you want it to do. So we had a reason to believe this would work. In one dimension, only 255 cellular automata rules show a ton of diverse behavior, anything from a pattern dying immediately to being able to simulate like a universal Turing machine. So in 3D, there's just way more opportunity for complexity. And that means a higher chance of specific rules meeting constraints for things like strength, flexibility, and material usage, which we define as metrics in our program. And overall, we achieve this by representing 3D cellular automata using a voxel-based system. And then we applied all sorts of like filters on this to get useful patterns. For example, specifying that the voxels need to be this interconnected, but have this sort of density to model things in real life. And then we use the marching cubes algorithm to take these discrete voxels and then turn into a continuous 3D shape that in like a standardized STL format. And then once it's in a standardized format, we were able to just put it into like standard 3D printer software and print it and see that our patterns actually worked in real life. And it's not just like a theory. So on the next slides, we're going to explain the more specifics on how we did all of this.
So I'll talk about the generating 3D cellular automata part. So I'll first introduce how we represent the rule in our project. So our current 3D cellular automata state can be represented like as a volume, right? It's like a 3 array, and each cell can tell this pattern of like the surrounding cell, and through each revolution step, we can just follow the pattern. Like if the pattern is the pattern that it intends, then it'll be then the cell will be filled as 1 in the next step. Otherwise, it will be 0. So each voxel in our state, which is also just like a 3D cell, will be we only consider its neighbors in 1 cell radius, which is a rule that we uses because like in other 3D cellular automata, like you can also do the radius with 2 or even more. But like in our program, we only use the 1 cell radius. And we also use this totalistic cellular automata, which is a rule depend on only the cell count in active neighborhood, but not the arrangement. And other types of pattern, and this allows us to reduce the complexity of our program overall. So the accomplishment of this, we implemented a function called cellular automation, which can just use to apply the rules for our cellular automata representation. Next.
Yeah. So in order to the end goal of our project is to basically take an arbitrary shape like the Eiffel Tower and use the cellular automata to make a shape for it. But if you just keep searching through cellular automata, what you'll find eventually is that none of them are just naturally in the shape of the Eiffel Tower. So instead, we need to create these kind of boundary conditions where we chop off the parts that aren't needed for the shape and then keep everything else. So you can kind of imagine like a honeycomb shape. It has all of the good structure on the inside, but if you chop it off and make it into a different shape, like a sphere, the inside of that sphere still has all the nice honeycomb structure. So we're not losing the complex cellular automata shape that makes the patterns like so strong. We're just adapting it for our purposes. And the way we basically did this on like a technical level was we created a bit mask. Or first, we let the cellular automata evolve in a rectangular prism shape. So, for example, if we were trying to print the Eiffel Tower, we would create a bounding box in the shape of a rectangular prism. And then basically just the way Wolfram handles cellular automata, this would have like a cubic boundary condition where basically if you can see those like faint gray outlines, if a cell went off the side of one of those faces, it would basically just wrap around to the other side on the opposite side of the prism, kind of like a Pac-Man game. So we evolve the cellular automata until it basically grows to fill that prism. And then we apply a bit mask where all the zeros chop off. Anything in the bit mask that is a 0 will be sliced off. Anything that's a 1 will be kept. So here are like kind of our basic geometric proof of concepts where we are actually able to define a bit mask like mathematically. So in a sphere, we basically had a matrix. It was like if the x coordinate squared plus the y coordinate squared plus the z coordinate squared is less than the radius of the sphere, then have that element be a 1, otherwise have it be a 0. And then we just applied that bit mask to the shape, and then we were able to take any arbitrary cellular automata and conform it to a sphere or a cylinder or a prism. But we need a way to do this with arbitrary meshes, which is what Austin will explain on the next slide.
So I'll talk about the voxeler function. So before running a cellular automata on a given shape, we cannot directly make the cellular automata to run on the 3D mesh in Wolfram language. So to do this, we first need to convert the geometry into voxels. So that's why we had our voxeler function here, which discretizes any 3D mesh in Wolfram language into a grid of small cubes, and each cube later on becomes a cellular automata cell. So here we had a parameter called resolution, where the higher resolution means smaller voxels and which can give us a finer geometric fidelity. So that means we can apply our cellular automata even on complex curve models or any given 3D models in Wolfram language. So on the left side, the image here, you can see a triangular mesh, and on the right side, is a voxelized version we had after putting in the Pris 3D mesh into our function. So our cellular automata rules then can operate directly on this voxel grid. And this function makes our approach very general. That means it can work for any 3D model representable in Wolfram language. I'll then talk about the matrix part of our project. So to compare any two cellular automata generated infill structure that we made, we needed to quantify the shape into some matrix, so that we needed some quantitative matrix. So here we had two matrices. One is called the infill percentage, and the other one is called the connectivity. So infill percentage is simply just the ratio of filled voxels, and it measures how much material that the model uses when printing. And this is important because it tells us the efficiency and the time to print. You don't want pretty much material because it will like waste the plastic that it uses, and you also don't want too less materials because it will make the model that it prints very weak. And on the other hand, we also have the connectivity matrix, which measures how well the fill voxels are structurally linked. It can tell us the strength and the printability of the shape. So we compute the connectivity matrix mainly using an algorithm called breadth first search, which just filters out the disconnected part of the shape and only count the ratio of the largest connected component from the volume of the whole model. And in the image below, for example, we have several different matrix value for different shapes. So the first shape has about 35 infill percentage, and this with 100% connectivity rate, which is the ideal matrix that we want for this cube shape. And the rest of them either may have more material or lower connectivity, meaning wasted plastic or weak bridges. So this matrix helps us to pick up which infills and are physically worth printing and testing. Yeah, next slide.
So now that we have the ability to basically evolve any arbitrary cellular automata rule and have it be contained within any arbitrary mesh, now we have everything we need in order to basically select for the specific infill pattern we want or our use case. So the way we do this is with a brute force algorithm. So if we take the overall rule space we want to search, we basically is going to have a minimum rule and a maximum rule. Doesn't really matter what we search. And then to make it faster, we do parallelization. So we just take this overall range and we split it into n groups, where n is the amount of threads or processes we have searching at once. And then within each group, we just evolve the cellular automata for a certain amount of times, and then run the infill metrics on it, and then basically see how close it is to what we want. So you can kind of see this in at work at the code at the top. So we have the optimize function where the first argument is how many rules we're searching. So our rule space is going to consist of 100 randomly selected rules. And for each rule, we're going to evolve it 30 times. So there's a trade-off here where if you evolve less times, then maybe you don't get to see what the overall pattern will evolve to. So maybe the first 10 evolutions of a rule is just a solid cube, which is not very useful. But then if you keep evolving, you might find that solid cube was just part of this, was just the center portion of this really complex structure that has all the properties you want. So you might end up missing stuff if you put this number too low. But if you put this number too high, then you're going to be wasting a lot of computation, just evolving this maybe larger than it needs to be. And then the next modular option we have is the shape. So here we chose Prism, but with how modular Wolfram is, we could literally just go to the docs, search up pyramid, copy a pyramid and put it there, and then our shape would be a pyramid, and all of these things would look like pyramids instead of cubes. So it's very modular that way. And then the bounds, 20. This just means that our rectangular prism is just going to be a cube with 20 voxels across on each side. Sorry. And then we have our info specification, where the first parameter means we want 10% infill. So basically 1 out of every 10 voxels is going to be filled in the whole cube. And this corresponds directly to the infill percentage in a real slicer, where, out of a certain volume, this much is filled with plastic. And then the 0.01 in the second parameter means that we're willing to go plus or minus 1% when we're selecting patterns. And then the connectivity is a low. It's like the minimum of what we want. So 0.95 represents that each pattern we want to be at a minimum of 95%, because we don't lose anything if we go above 95%. The patterns just get stronger. So this optimize returns just a list of a bunch of matrices representing which patterns fit these specifications, and then we mapped array plot on it. And this is basically the core interface for how a user uses our algorithms to get a 3D printer pattern that is suited for their needs.
So we also had a visualization function used to visualize the infrastructure that we generated using our function. So each 3D cellular automata evolution is stored as a 4D matrix, where 3 of them are spatial dimensions plus a time dimension, which is and this allows us to visualize how patterns grow over iterations. So our visualization tools let us to explore individual time slices to study how our the infill structure grows. So here we also implemented 2 different functions called isolated parts and connected parts. As you can see in the image, there's a display mode. There's a regular view regular and a view isolated. So this can automatically detect the floating voxels, because those floating voxels are unprintable. So we can isolate them visually. And if you look at the image, that's the visualized 3D matrix, which is the function for our visualization interface. And we can adjust the dimensions, slice index, and switch between the regular and isolated view modes. And they also displays the live infill and connectivity matrix below. Yeah, and if you go to the next slide, there is like a video that I recorded how the visualization works. I guess we can just skip it.
Okay, so like I mentioned at the beginning of the presentation, once we have this kind of intermediate voxel representation, we need to turn it into something that can actually be printed. So there was actually a very, very handy Wolfram function to do this using something called the marching cubes algorithm. I believe this is used in other applications, such as like in like an MRI scan or something where there's like a lot of like discrete points that need to be turned into like a continuous 3D mesh. So we take whatever pattern the user selects, and then we transform it into an STL, and then the workflow is pretty simple from here. You just put it into your favorite slicer, and then end up actually printing it in physical material on a printer. So you can see in the last image, that's what the actual we're able to actually slice this as part of a cube. So the pattern shows all of the material that was removed in order to save material. And the overall goal of this gist of this project is that this pattern, even though it looks really complex and maybe looks intelligently designed, was actually just the result of searching through a bunch of rules. But overall, it still achieves the same purpose of what the user wanted. It only uses up 20% of the volume, so you save material. It's still just as interconnected and complex as a procedural, like a industry standard infill pattern, but it's able to be a lot more specialized to what the user wants, based on optimizing on those like metric functions we defined earlier.
I can talk about this part. So after evaluating our Sarah Tomta generated infill structure with digital metrics like the infill percentage and connectivity, we also wanted to see how they perform in real-world 3D printing. So the print time was pretty comparable to a traditional infill pattern of the same size, which means our method didn't slow down the printing process pretty much. And we also checked the for the overhangs, and they were small enough that the printer could handle them without any additional support structures. So as you can see in these two images, the first one was the midway through at like a 30% completion, and the other one is the final printed cube. And the structure was pretty solid and also noticeably lighter than like a normal print things, which is a pretty good balance between strength and material use. And overall, our 3D Sarah Tomta generate patterns are not just theoretical, and they work very well. Yeah.
So the demonstrated impact was we were able, like I said on the previous slide, we were able to find a 3D printer infill pattern that was not programmed up by anybody in specific, did not rely on any sort of human intuition, and yet still achieved all the same things as a standard 3D printer infill pattern, and has the potential to achieve things way more specific with the billions of patterns we search through compared to the maybe 20 generalist infill patterns that are meant to be mediocre at a large range of tasks instead of really good at your specific task. So you can imagine the overall workflow at being, if we had a little bit more time to work on this, instead of you selecting like a predefined infill pattern, instead you give your shape to our program, and the program says, okay, what do you want? What do you want from the infill pattern? Do you want it to be flexible? Do you want it to be strong? Do you want it to be light? Things like that. And instead of you searching and finding the infill pattern you want, the program will actually find one for you that maybe didn't exist anywhere before. Nobody's ever used this infill pattern, but it happens to be the exact right one for your print. And any other users with any slightly different configuration of 3D print or metrics would get a different infill pattern that probably also didn't exist before. So our work really enables the transition between like generalist patterns to really specialized patterns. And our future work would probably mostly relate to like adapting this into a full workflow so that it doesn't even require Wolfram to run. It's just like a built-in plugin into popular slicing software. And I think that is it.
Well done. Fantastic. Good coping with tech issues too. Great. This is really cool. Well done. While maybe one or two people want to ask any questions in the... Oh, we have one already. Satyrus says, have you examined if chaotic rules produce better infills compared to predictable or regular pattern producing rules?
I'm not exactly sure what chaotic means here. Something we were planning to explore was all of our, because like cellular automata is all deterministic. So I'm not sure if chaotic means like implementing like randomness into it. But one way we maybe thought of doing that is with like random initial conditions. So what we were doing is just like using a single black cell as the initial point, and then because cellular automata has kind of emergent complexity, it doesn't really matter if your initial condition is basic; it'll still kind of grow into something very complex. But we still achieved good results this way. But we were wondering whether maybe having random initial conditions would maybe be able to exploit some more complexity and find some more different patterns. So I think yes, we were considering adding a little bit of randomness to our work in that way with the initial conditions.
Also, I think we have tried many different initial rules as well, and some of them are just random, but like most of them just stops evolving after a certain point, which is not the thing we want because we want a structure to be filled with cells, right? So in the end, just like a limited number of rules that works for our project.
Nice. What was the most challenging or craziest thing that you learned or accomplished or struggled through?
I think like the most surprising thing to me was just I mean as far as how challenging things were, I think probably the most challenging thing we did was define the metrics. Austin coded some pretty complex algorithm for the connectivity. But as far as like crazy stuff, I was really, really surprised that like how like good it all worked together. I don't know another way to explain it, but like our idea of just using the 3D cellular automata, but then seeing just like how complex and like honestly like kind of beautiful these patterns looked, but we're still able to print in real life. It's like it seemed very, very impressive for what we were able to do with kind of a limited amount of work and time with the Wolfram language.
Very cool. Awesome. Well done. Okay, our next group up is Annie, Tony, and David. And they are going to present their work about human protein interaction networks.
Hi everyone, I'm Tony Song, and today I'm here with Yoga Wang and Amy Zhu. And our project was on analyzing and visualizing the human protein interaction network, which we conducted during the 2024 Wolfram Emerging Leaders Program with our mentor, Dr. Sutik Slash.
Alright, so first we're going to go over what protein-protein interactions really are, and then we're going to go over the data, some visualizations of the network itself, and comparison with gene co-expansion networks, alpha emissions, pathogenicity, and cancer.
So first off, protein-protein interactions describe how proteins communicate with, of course, other proteins and function in our body. So each protein is capable of interacting with potentially multiple other proteins, and such interactions can range from direct physical binding to functional associations that contribute to complex biological pathways. So this emphasizes the interconnected nature of the protein networks in our bodies.
Studying these protein interactions can help us understand cellular mechanisms and develop therapeutic strategies. Techniques like co-immunoprecipitation, yeast-2 hybrid screening, and databases like the Human Protein Atlas allow researchers to analyze these networks, revealing the functional roles and interdependencies of proteins. These proteins are encoded for by genes, and in this project, we construct the complete human protein-protein interaction network, or PPIN, and analyze the graph values of this network, making connections to diseases and cancers.
Okay, so first off, we took data from the Human Protein Atlas version 24.0, which provided 90 different features for 11,251 genes coding for proteins in humans. These were attributes such as the chromosome number, the protein class, that were processed, and these were originally found in countless JSON files inside of the Human Protein Atlas API. So now you can, we uploaded this to Wolfram Data Repository, and that's where you can now find this data. So on the left, you can see that an entry for the gene C2 or 50. So this was a gene selected at random. And you can see some of the information that the Human Protein Atlas provided here. So one of the most important values here is the ensemble ID, which is one of the 90 attributes. So all of our keys in our data were in the form of these ensemble IDs. So they serve as unique identifiers, as one gene may have multiple names, but will only have one ensemble ID. Because this system is standardized and used by both the Human Protein Atlas as well as other data that we use, it allows for reliable cross-referencing throughout our work, making it easier for us to interpret and analyze the data. As for the actual protein-protein interactions, we also scraped that from the Human Protein Atlas, and these were created as lists. So on the right side, we have a screenshot of some of the interaction data. So essentially, you can see that, as stated earlier, one protein may have multiple protein-protein interactions. For example, the first one, A1CF, has 16, and the second one, A2M, has 51. And so using these interactions, we constructed the network in this graph by connecting the nodes of the proteins which interacted with each other. And we will continue to explore this network on the next few slides.
Alright, so here we begin with a couple of visualizations for our graph before we explore some interesting properties of a human protein-protein interaction network. So here on the top left is going to be a visualization of the human protein-protein interaction network consisting of giant interconnected graphs, small loops, and simple edges. And basically, this reflects the complex organization of protein interactions in the cell. And the giant interconnected graph represents the coding fractome, where most proteins are linked through direct and indirect interactions, enabling widespread communication and coordination of cellular processes. This large component facilitates the flow of information and the propagation of signals across the protein. Small loops and graphs likely represent functional modules of protein complexes that perform specific cellular tasks, allowing for localized and specialized functions. Probably the most interesting feature exhibited by the graph is the small Wolf phenomenon, meaning that the graph has a high clustering coefficient and low distances between nodes. The human, which makes it particularly interesting to investigate the role of hubs in relation to the biological functions, health, and disease. The small Wolf phenomenon introduces hubs, connected nodes, which may hold key insights into critical processes, including the stability of the network, disease propagation, and potential therapeutic targets. The top right graph has each node scaled by its degree, demonstrating how the graph mainly consists of a few nodes with many connections and many other nodes with few connections, exhibiting the small Wolf phenomenon. The bottom left graph colors each node by its distance to each hub, are showing in the top 25 nodes in terms of connections on the right, showing how most nodes are extremely close to the hub. And the histogram of node distance to hub is also demonstrated here, with the vast majority of nodes being within 2 connections of a hub. And all this is very interesting for analysis when thinking possibilities for future research on the significance of these hubs.
Here, I will show how we visualize specific proteins within a protein-protein interaction network. The function we created takes a protein gene name and a chosen depth as inputs, and then generates a graph corresponding the network. Depth 1 includes the target protein and its direct interactors. Depth 2 adds all proteins connected to those, and so on. Depth shows how far from a given protein we want to trace its interactions, and the right depth helps balance clarity with biological insight. At a shallow depth, we can only see direct interactions, which gives a simple and clean network for easy interpretation and great for identifying meaningful testing partners. As we move deeper, the network expands and reveals indirect or secondary roles that proteins might have. In disease or signaling contexts, these indirect interactions can be especially informative to show how proteins' effects propagate through a network. By adjusting the depth, we can explore protein interactions at the multiple levels of biological detail, from immediate connections to the wider system that they belong to. We can color code nodes by measures like vertex degree to highlight key proteins or interaction hotspots, making complex networks easier to interpret to reveal important clusters or functional patterns.
All right. So next up, we introduced gene co-expression networks, which is a graph where nodes represent genes and edges connect genes showing similar expression patterns across multiple locations, samples, or combinations. In contrast, protein-protein interaction networks represent physical interactions between protein molecules, with nodes representing proteins and edges indicating direct biochemical contents. Both network types are crucial for understanding cellular processes, with GCNs helping identify potential functional gene groups, and PPIs providing insights into molecular machinery and signal pathways. For this section, we introduced 4 different centrality measures, including local clustering coefficient, between centrality, vertex degree, and eigenvector centrality. All of these are ways to measure the importance of a node in a graph. Our main goal is to see if there's any correlation between the importance of a node in a PPIN and the importance of a node in a specific gene co-expression network. So we can see in the top left and bottom left corner, we see 2 graphs that demonstrate specific examples for certain pairing the centrality measure and gene co-expression network. The graph on the top left demonstrates the correlation between centrality in the protein-protein interaction network and centrality in the tissue gene co-expression network for all common proteins. The bottom left word cloud gives the genes that have high centrality measures in both the PPIN and the tissue gene co-expression network. In the other 2 tables at the top, we see smaller versions of this data gathered for each pairing of co-expression network and centrality measure for a total of 12. We can especially see that there's very limited correlation for importance in protein-protein interaction network and co-expression networks, for example. The bottom table is able to summarize the correlation between the centrality measures of the genes of the protein-protein interaction network and the gene co-expression network. As we can see, there isn't much correlation between different graph measure pairs. The lack of correlation between graph measures for genes and co-expression networks and the corresponding proteins in protein interaction networks can be attributed to several factors. For example, one such factor could be functional differences where co-expressed genes may be involved in similar biological processes without the proteins directly interacting, while interacting proteins may not necessarily be influenced by co-expressed genes. Another factor could be because gene co-expression networks present relationships with the mRNA level, while protein interaction networks represent physical interactions at the protein level. So these 2 biological levels can have distinct regulatory mechanisms and dynamics.
So we also did work to compare the human PPI in graph measures for genes and the average predicted alpha missense pathogenicity in the corresponding proteins. So first off, mutations are changes in the DNA sequence that can alter the way proteins function in the body. So proteins are formed from chains of amino acids, and a mutation can cause one of these amino acids to change. And even one altered amino acid can impact the structure and function of a protein. And this can sometimes lead to diseases such as cancer or genetic disorders. So alpha missense, which was developed by Google DeepMind, is an advanced AI model designed to evaluate missense mutations, which is when a single amino acid in a protein is replaced with another. These mutations can, again, vary from being harmless to severely damaging. So building on the structural prediction technology from AlphaFold, alpha missense uses large-scale protein structure and genomic data to predict whether a given mutation is likely benign or harmful. And then they will provide a we can compute a pathogenicity score for any missense mutation at any amino acid position in a human protein. So for each amino acid in the protein sequence, we can replace it with any of the 19 other amino acids. And each of these will produce a pathogenicity score, which we can then find the average of to determine the mean pathogenicity for a mutation affecting a certain amino acid. For example, in the image on the top left, generated by missense variant plot 3D of functioning Wolfram, the red sections have a greater mean pathogenicity, and the blue sections have a lower mean pathogenicity. That mutations in the red parts are more likely to be pathogenic than mutations in blue parts. So for us, moving on, for a given gene, we can calculate two overall values that can indicate the overall pathogenicity. So our first one was the average mean pathogenicity score, which for the entire protein. So we obtained this by averaging the values of mean pathogenicity for every amino acid in the sequence. And our second value that we calculated was the fraction of likely pathogenic mutations. So for each different mutation going from one amino acid to another amino acid, we can categorize into one of three categories: likely benign, ambiguous, or likely pathogenic. And then from this, we determine the fraction of these mutations that are categorized as likely pathogenic. We then look to see if there was any linear correlation between the graph measures of the protein-protein interaction network and the two values that we just calculated. However, this does not appear to be the case from both the correlation values and just simply looking at the graphs on the right. So, however, we can still see the clustering of the graphs, which is likely from the human PPI and graph measures themselves. So while we didn't find strong overall correlations between predicted pathogenicity and the PPI and graph measures, we can do further analysis on specifically chosen proteins, which may reveal more meaningful relationships inside future research. So we also calculated some word clouds for these to determine which genes and their corresponding proteins are most important for each combination of these two.
Alright, so next I'll be talking about how protein-protein interaction networks relate to gene expression and cancer patient outcomes across multiple cancer types. By integrating network measures with mRNA expression and survivor data, we aim to uncover potential links between a gene's network role and its impact on prognosis. Here on the top left, we compare the distribution and expression of genes across cancers as well as prognosis for specific cancer types in relation to gene expression. This analysis will later be integrated for protein-protein interaction networks to explore these potential links and cancer outcomes. This first graph shows the mRNA expression levels for each cancer type and the distribution expression for a specific gene, ITGA5. The graph illustrates how ITGA5 expression affects survival in renal cancer. Patients surviving beyond 40 years after diagnosis generally had a lower expression levels, suggesting a potential role for this gene in disease progression. You can see this in the top right with the alive marked as blue and dead as marked as red. To test whether the differences in the expression between surviving and non-surviving patients were statistically significant, we used the Pearson chi-square test. A smaller p-value, typically below 0.05, indicates that the distribution is likely significant. In renal cancer, as seen on the bottom graphs, the expression of distribution of ITGA5 between alive and deceased populations were significantly different. In contrast, in breast cancer on the right, no clear difference was observed, indicating that the impact of this gene may be context-dependent. Next slide, please. Next, we compared these p-values with various PPI and graph measures. Earlier, David explained 4 of our graph measures, except here we also added 2 new ones, which are the radiology centrality and the local clustering coefficient for more analysis. Generally, correlations above 0.7 mean meaningful relationships. And across the cancers, eigenvector centrality showed the strongest correlation with p-value. And this suggests that proteins connected to other highly influential proteins have a greater effect on cancer outcomes. Many cancers followed similar trends, though some outliers, such as stomach cancer, were observed. Reversing the correlation direction confirmed these patterns. Despite these observations, most correlations between the protein interaction measures and the gene expression of p-values were weak or absent. As you can see, the highest is about 0.05, which is really low. This likely reflects the complexity of cancer biology, which involves multi-level regulation, including gene expression, epigenetics, and environmental influences. This often interacts in ways not captured by the static protein interaction networks. Graph measures like centrality or clustering are generalized and may miss context-specific roles of genes in cancer pathways. Standard protein interactions networks may also include false positives or miss critical cancer-specific interactions, and dynamic changes in protein expression may occur on timescales not reflected in the network.
Okay. So looking forward, our work with the protein-protein interaction network lays the foundation for, again, future work towards goals in systems biology, including building dynamic or tissue-specific networks, studying disease-specific interactions, and potentially and applying machine learning to potentially uncover hidden patterns. And this may also allow for potential and even personalized medicine. We would like to thank Dr. Sudik Saha for his unwavering support, mentorship, and invaluable guidance throughout this project. His insights were instrumental in shaping the direction of our work. We would also like to extend our thanks to the program directors, Rory Folger and Aaron Gillum, for establishing the framework that made this program and our work possible, and for providing us with this amazing opportunity. Thank you.
Thank you. Well done, guys. Okay, we have a question from Sataris, which says, have you tried recognizing modules or communities and seeing how they correlate to functional units, like being related to a specific body function, or pathology, like proteins involved in a specific disease forming a community or module in the network?
We haven't tried that yet, but it seems like an extremely interesting suggestion that's really related to science. And I think I'd be really interested to try it in the future and see if there's any correlation there.
If we had more time to do work on this, we definitely would have done something similar.
Yeah. Awesome. Fantastic. Right there. What was the craziest or most difficult thing that you did in this project?
Oh, I think this kind of answers the question also, because Wolfram had very limited protein functions, and recently we had a lot of updates with these structures and all that. I think before we were sort of limited to only taking data from other sources and then using graphs to do this. Except now with new Wolfram features, we look forward to maybe connecting these with 3D structures and 3D interactions, which would be really interesting to look at.
Yeah, very cool. Very cool. Okay, well done. So our final presenter of the day is Ethan.
Hi, so my name is Ethan. I did this project in WSRP 23. Wait, was it 23? No, 24. WSRP 24. And I did an optimization of electric thrusters. And so what are electric thrusters? There are two main types of electric thrusters. And electric thrusters are basically rocket engines that are used in satellite orbits to provide very low amounts of thrust for attitude control. What differs electric thrusters from normal rocket engines is that instead of combusting a gas to exhaust out the nozzle, electric thrusters they ionize a particle, a heavy particle like xenon or like argon, and then they exhaust it out they accelerate the particle up to speeds of 120 kilometers per second with electric fields and magnetic fields.
and through that they are able to have much higher specific impulse, which is fuel efficiency. They are able to have much higher fuel efficiency than standard rocket engines with specific impulse up to like 3,000 Newton seconds compared to like 350 for like the current most efficient rocket engines. But an issue, so there are two main types of electric thrusters. There's on the left here is a gridded ion thruster. On the right here is a Hall effect thruster. Gridded ion thrusters are type of electric thruster that ionizes the gas within the within an anode chamber, and they use magnetic rings and just an electric negatively charged electric field to keep all the ions inside the chamber to be collided with an electron gun that's emitted by a hollow cathode on the left. And once the atoms are ionized and turned into plasma, they are accelerated through like a positive and a negative grid here that are very closely spaced together. And through that, when the ions pass through, they are accelerated up to huge speeds and are able to just generate a bit of thrust. Similarly, with the Hall effect thruster, the Hall effect, as the name suggests, it uses the Hall effect to cause the electrons to spin in a circle, and by doing so, the electrons are able to collide with much higher amounts of the propellant, and is a bit more efficient with the propellant usage, and but it has lower exhaust velocity. So what's the current problem with ion thrusters? One big issue with them is that they use a lot of electricity to run, and they produce extremely low amounts of thrust in the orders of like hundreds of millinewtons in comparison to like Raptor, which is like megatons, so like they have like millions of newtons of thrust. But then Hall effect thrusters, they're producing like 750 millinewtons per like kilowatt of power. So they're very expensive to run, and they generate very low amounts of thrust. So my project was to find like the perfect parameters to optimize the thrust to power consumption ratio, to find like for what physical parameters, like the screening grid, like how thick can the screening grid be, how big should the anode region be, how strong should the magnets be, to generate the most amount of thrust with the least amount of electrical power. And so my research consists of like three main parts. I had to create the physics simulation and to calculate the trajectory, the thrust, and the power consumption, and then I could do optimization I can do a grid search to find the optimal parameters. In order to create the simulation, I first had to define all the different regions. The top left image here, that's for the Hall thruster. The bottom left is for the gridded ion thruster. You can see I had like the screening grid and the acceleration grid, and also like the anode region I would define within Wolfram using parametric plot 3D. And here I have like plasma regions, magnetic regions, like a north magnetic region, a south magnetic region. You see like red and blue if you can see that. And I would, within all these regions, I would assign the electric charge assigned to like the anode and the cathode. I'd assign like a magnetic field strength that I could then plug into Poisson's equation here to find the electric field at any given point within the simulation. And then I could also find the magnetic field given the strength of the magnet, how much current we're flowing through the magnet. So with that, we're able to find like if I'm flowing 50 amps, I would be able to see this many Teslas, this many newtons of this many Teslas of electric magnetic field strength, and I'd be able to calculate, oh, this is how much power I'm consuming. Similarly with the electric field, I'd be able to calculate the electric field strength based on the power consumption. And so here I just defined so defining these regions, the different parameters I optimized for were like the anode,
like the size of the anode, the screening, like the radius, the thickness, the height, the length. You'd have like anode, the cathode radius, you have grid spacing, grid height, like size of the magnet, size of the how long the thruster is. And in order to calculate the trajectory, I used forward Euler integration, which I now realize is actually not which now in university I've learned more different methods I'll talk about that would have been smarter to do. I just calculated all the forces acting on the on one specific ion, and just use for Euler integration to calculate the trajectory, to simulate the trajectory of the ion as time went on. I just have the x direction, the y direction, the z direction of like the magnetic field strength and the electric force and the magnetic force to push the particle and calculate the velocity over time. And so here are some I had some graphs of some this was for the gridded ion thrusters on the left. It's able to go up to 120 kilometers per second, and the Hall effect thruster on the right, it goes up to like 20 kilometers per second. So like I said, Hall effect thrusters have lower they have lower exhaust velocities, and so but okay, so I know it's and so in the end, with my results in comparison, I was able to compare. I was able to find some research paper from the Michigan's plasma electric propulsion lab, and I was able to compare the velocity profile with their empirical data with my simulated data. And while we can see the velocity profile doesn't completely match for using the same parameters that they set with and I also set, we're able to see if we ended up at a similar exhaust velocity, but mine doesn't account for plasma friction or the ionization process, which is why the first half of the velocity profile looks quite different. I was then using the simulation. I then ran grid search over a lot of plausible parameters that I used research to just find like, what is the minimum size of the anode? What's the maximum size of the anode? What's the minimum radius? What's the maximum radius? I used grid search to pass through over like thousands of parameters, and through that I was able to calculate the thrust and the power consumption of each combination of parameters, and I was able to create a correlation matrix between like thrust and like anode radius and like thrust and power consumption. And as you can see, I think this one is for the Hall effect thruster because there's no grids. And you can see like, by increasing the anode thickness, we're able to there's a huge negative correlation with thrust to power ratio. So we want the anode to be as thin as possible, and we're able to understand these correlations. And in the end, I was able to find a thrust to power ratio for a gridded ion thruster of around 14 kilowatts per Newton. And this is almost like double the efficiency of NASA's current like best most efficient Hall effect thruster, a gridded ion thruster, which has a power efficiency of 30 kilowatts per Newton. And for Hall effect thrusters, I was able to find a power to thrust ratio around like 10.6 kilowatts per Newton, which is also significantly better than European Space Agency's 17 kilowatts per Newton. So in the future, I think what I would want to do was is to implement better particle push methods. Like I recently learned of like the Boris method of particle push, where we, instead of taking a solid time step and integrating over each delta t, we would find a delta t over 2 and find the velocity, calculate the velocity at that time step instead of immediately jumping to the next one. And that would be able to, that creates the Bohr's method is the golden standard for particle plasma physics in the academic world. And that would be interesting to see how my results compare if I use the standard method. And also I need to account for the plasma friction and ionization process, as I never did that in my research. And I would like to explore like dual stage thruster designs where you can have like a separate ionization zone and an acceleration zone, and see if those are more power efficient. Yeah. Thank you.
Excellent. Very cool. Okay. Great. While we're seeing if anybody has any questions for that, what was the hardest thing or most difficult thing that you came across doing this project?
I think the hardest thing was I didn't have any experience with plasma modeling and like any like space, like aerospace engineering and experience before starting this, and to basically learn a lot about plasma dynamics and learning about how Hall thruster works, how to properly model it accurately, and learning how to compare, just learn about the research process and comparing my simulations with like empirical data. That was quite difficult, and I want to thank like Sheng Wei, my mentor, that was able to like teach me all of that really effectively.
Amazing. And Jason asks, you mentioned an improvement in approach that you've learned about recently. Is that feasible for you to implement in Wolfram?
Yeah, definitely. Because basically, I can the Bohr's push method. This is over here, the Vn plus 1 over 2 minus Vn minus 1 over 2. It's very similar to what is basically my current method. What I'm doing is the one here, dv over dt is just t over m e plus b cross b. Basically, as all I need to really do is change within the acceleration the equations of motion. I just need to add a separate temporary variable to calculate the velocity at like a time step in between the current time step and like halfway between the second time step, and it would be pretty simple to implement in Wolfram.
Yeah. Nice. Very cool. Amazing. And you published a paper on this, right?
Yeah.
Yeah. Very cool. Very cool. Okay. Thank you so much, Ethan. And thank you everybody for coming to this session. I hope you had a great time getting to know some of the amazing projects that our students have done over the last couple of years. And, if you were particularly excited about it and you'd like to come and mentor for one of these programs, we'd love to have you. Just reach out to me. And if you have kids who you think would be really interested in it, we'd love to have them.